Today I'll solve one numerical example on limiting an excess reactant, fractional conversion and extent of reaction. So here is the problem. Problem is oxidation of ethylene to ethylene oxide. So here is the reaction equation, 2C2H4 plus oxygen. So that will give 2C2H4O. So ethylene is oxidized and produce ethylene oxide. Now here given data, the feed to a reactor contains 100 kilomole of C2H4 and 100 kilomole of oxygen. So in that reactor feed ethylene and oxygen, so both are 100 kilomole. Then first question was which reactant is limiting. Then what is the percentage excess of the other reactant, and if the reaction proceed to completion, how much of the excess reactant will be left, how much C2H4O will be formed, and what is the extent of the reaction. And question number 4, if the reaction proceed to a point where the fractional conversion of the limiting reactant is 50%, how much of the each reactant and product is present at the end, and what is the extent of the reaction. And if the reaction proceed to a point where 60 kilomole of oxygen is left, what is the fractional conversion of C2H4 and fractional conversion of oxygen, and then finally the extent of reaction. So now I'm going one by one. So first, which reactant is limiting? So first I have to find out the limiting reactant. First, so stoichiometric ratio, first I have to find out from stoichiometric ratio. So equation is given 2C2H4 and oxygen. So stoichiometric coefficient for C2H4 is 2 and oxygen is 1. So now stoichiometric ratio C2H4 is to O2, that is 2 is to 1. Now feed ratio, both reactant enter in at the reactor, that is 100 kilomole 100 kilomole. So feed ratio of C2H4 and oxygen, that is 100 100, 1 is to 1. So stoichiometric ratio of C2H4 is to oxygen is 2.1 is greater than feed ratio of this. So here C2H4 is limiting reactant, because if you take one both side 1, okay, so stoichiometric ratio is 2, so 2 is not there, obviously C2H4 is the limiting reactant. So now if C2H4 is the limiting reactant, then calculate moles of oxygen needed, right? So here 100 kilomoles is the limiting reactant, so 100 kilomoles limiting reactant. So now kilomole, so from this kilomole, so from this stoichiometric ratio we can easily calculate how much oxygen is needed. So that is the ratio is here 2 is to 1. So 2 mole of ethylene react with of 1 mole of oxygen. So here 100 kilomole is the limiting reactant, so oxygen required by 2, so 50 kilomole. So that is there. Now next is percentage excess of the other reactant. We have to calculate what is the percentage excess of the other reactant. So percentage excess of oxygen, so actual mole minus percentage excess formula is actual moles minus stoichiometric moles by stoichiometric moles into 100. So here percentage excess is oxygen, so actual mole 100, stoichiometric is required 50 and stoichiometric 50. So 50 by 50 into 100, so 100%. So oxygen has 100% excess. So third number question, so if completion of the reaction, so what will be the, so question number 3 here. So if the reaction proceeds if the reaction proceeds to completion, how much of the excess reactant will be left, how much C2H4 will be formed, and what is the extent of reaction. So for that, so first, if the reaction proceed to completion, so all C2H4 will react and none will be left, because C2H4 is limiting reactant. So moles of C2H4O formed means moles of C2H4 feed. So here stoichiometric reaction is like 2C2H4 plus oxygen, so that will give 2 C2H4O. So 2 moles ethylene form 2 mole ethylene oxide. So moles of C2H4O formed is equal to moles of C2H4 feed, because all C2H4 react. So 100 moles actually feed, so 100 kilomoles. Now excess oxygen. So actual excess oxygen means actual moles of oxygen minus stoichiometric moles of oxygen. So now, so as how much amount of oxygen required, so that will be 50, so that is 100 minus 50, so 50 kilomole. Now extent of reaction at completion, so that is formalized Ni minus Ni0 by nu I. So then that means moles of reacted by stoichiometric coefficient. So here if I consider the oxygen, so moles of oxygen reacted and stoichiometric coefficient of oxygen. So zeta is xi by xi, not zeta, xi, 50 by 1, so 50 kilomole. So now question number 3 is answered. Now if the reaction proceeds to a point where the fractional conversion of the limiting reactant is 50%, so how much each reactant and product is present at the end, and what is the extent of reaction? Now 50% of the limiting reactant, so 100 kilomole of limiting reactant feed, so 50% conversion, so F is equal to 0.5. So moles reacted 50 kilomole, so 100 into 0.5, so 50 kilomole. Moles unreacted 100 into 1 minus 0.4, so 50 kilomoles. So moles of oxygen reacted, so half into moles of C2H4, because ratio is stoichiometric ratio C2H4 is to oxygen, so that is 2:1. So moles of oxygen reacted, so half of moles of C2H4 reacted, so half of 50 kilomoles, so that is 25 kilomoles. So moles of unreacted, so 75 kilomole, means that is present. And then moles of C2H4 formed, so that is equal to moles of C2H4 reacted, so that is 50 kilomole. And extent of reaction, so moles reacted C2H4, stoichiometric coefficient of C2H4, so that is 100 moles reacted, no, so that is, this is here wrong, so 50 moles reacted, this is 25. If you take the oxygen, so oxygen reacted is 25, so if you consider zeta, so that is 25 by 1, so that is 25 kilomole. Now question number 5, if the reaction proceeds at a point where 60 kilomole oxygen left, what is the fractional conversion of C2H4 and fractional conversion of oxygen and extent of the reaction? So now 60 here, if the reaction proceeds at a point where 60 kilomole of oxygen left, then moles of oxygen reacted is 100 minus 60, so 40 kilomole. So moles of C2H4 reacted, so 2 into moles of oxygen reacted, so that will be 2 into 40, so that is 2 into 40 means 80 kilomoles. So now moles of C2H4 unreacted, so that is 100 minus 80, so 20 kilomoles. Now fractional conversion of C2H4, so moles reacted by mole speed, so mole reacted is 80 by 100, so that is 0.8. Fractional conversion of oxygen, mole reacted by mole speed, so 40 by 100, so 0.4. And the extent of reactions, mole reacted of C2H4 and stoichiometric coefficient of C2H4, so 80 by 2, that is 40 kilomole. So I think that's it for this problem.